Good morning, welcome to new lecture. Today I will talk about more about area moment of inertia and radius of gyration and polar moment of inertia. Let's review what we had last session. If for example we want to use one beam to cover one span, for example it is simply supported beam, we use beam in order to cover this span, and here we have one load, for example it is 200 pounds. Assume this is for example 10 feet beam, and the lumber we bought it, and the cross-sectional area it is 2 inch by for example 6 inch. I can put lumber or beam in this direction, so it will bend respect to this axis, or I can rotate it and I can put in this direction. 2 inch, 6 inch. In this case it will bend respect to this axis. If you do simple experiment, you will see beam in this direction is much stronger. It will show less sagging or deflection, and it is more stronger, and it resists against bending moment more. But the cross-sectional area is the same material, for example wood is the same, everything is the same. Only the direction will change. The reason the area moment of inertia or second moment of area or simply moment of inertia in this direction is much greater than this direction. From here, if you remember, I defined and I said the further the material spread from the bending axis the stiffer a cross section tends to be this concept of resistance to bending can be quantified by calculating the moment of inertia and I talk and I explain in order to calculate the moment of inertia for one cross section, something like this, respect to those axes passes through centroid. For example, point C is the centroid, this will be XC, this will be YC. I will assume one small element. The area for this element it is dA, and moment of inertia IXC is equal to integration of the distance of element up to x-axis, which is y squared dA, and the moment of inertia of this element respect to y-axis, it will be x squared dA. And if I want to calculate for entire cross section, I should integrate that. So if I assume one element, the distance of this element from y-axis it is x, from x-axis it is y, the moment of inertia for this element respect to x it will be y squared dA. If I want to calculate for entire cross section, I should integrate it for entire cross section, and the moment of inertia for this element respect to y-axis it will be x squared dA. And again, if I want to calculate for entire cross section, I should integrate for entire cross section. This is the definition of moment of inertia. And the moment of inertia unit, you see from here, the moment of inertia unit, it will be length unit to the power of 4. For example, it will be millimeter to the power of 4, or centimeter to the power of 4, or meter to the power of 4, or inch to the power of 4, or feet to the power of 4. So the length unit to the power of 4 will be the unit for moment of inertia. So if I calculate the moment of inertia respect to those axes passes through the centroid, I can calculate moment of inertia respect to any other axis which is parallel to this. For example, another axis, it is x and it is parallel to the xc. If I want to calculate moment of inertia respect to the x for that cross section is equal to moment of inertia of that cross section respect to xc. Pay attention, these two, they should be parallel, plus entire area for cross section A times the distance between these two axes d squared. And this relation I call the parallel axis theorem. The parallel axis theorem. Then, if you remember, I emphasized this moment of inertia we will use in static and strength of material and structural analysis, and it is different from mass moment of inertia. This is area moment of inertia. In the dynamic course or physics, we have another moment of inertia, that is mass moment of inertia. And I define that, again I will define one more time, and I will emphasize on that. The area moment of inertia should not be confused with the mass moment of inertia, which is a parameter used to describe the resistance of a body to change in rotational velocity. So the area moment of inertia should not be confused with the mass moment of inertia. Mass moment of inertia we will use in dynamic and physics, which is parameter used to describe the resistance of a body to change in rotational velocity. There is similarity and difference. Both is denoted by I. But if I write, this is for example area moment of inertia, mass moment of inertia. Both is denoted by I. Here the formula I is equal, for example, y squared dA. Here I is equal to, for example, r squared dm. Here is differential area, here is differential mass. Unit for this, for example, millimeter to the power of 4. So length unit to the power of 4. Unit for this, it will be mass unit times the unit of dimension or length again to the power of 2. For example, kilogram times meter squared. Here the length unit to the power of 4. Here mass unit times the length unit to the power of 4. This is mass moment of inertia application in physics, dynamic, any place we have motion. Area moment of inertia in static, strength of material, we don't have motion, but we want to find resistance against the bending force, bending moment or shear force and so on. Later on, in mechanics of material course, in order to find deflection or deformation of one beam, for example, we have one beam and this beam is subjected to bending moment M. This beam will bend and it will deform. In order to find deflection or deformation, I will prove later on one formula. Second derivative of y respect to x is equal to bending moment divided by EI. I here again area moment of inertia. E is Young modulus or modulus of elasticity. Later on I will define those. You see has application in strength of material. EI here we call it flexural rigidity. So here we call EI both together flexural rigidity. This is the application of area moment of inertia. In order to find deflection or deformation in one beam, it's subjected to moment or load. For example, this is a straight beam. If I apply moment M and M, it is clear this will bend. This deformation Y I can calculate using this formula. Or if I have column, in one column, if it is long column, if I apply load and if I increase this load from 0 step by step, suddenly in one certain amount of load, we will call it critical buckling load, this column will buckle like this. The critical buckling load later on you will see we will calculate using Euler formula, which is pi squared EI KL squared. Again, I moment of inertia, but it is area moment of inertia. EI flexural rigidity, pi it is number pi, K depend on the support condition, it is number, L it is length of the column. And if we want to calculate the critical stress, that will be equal to pi squared E divided by lambda squared. And the lambda we will define as a KL over R. Here R is radius of gyration. Radius of gyration. Later on we will need that in order to calculate the buckling load or buckling stress for one column. This R, we call it radius of gyration. And we will define radius of gyration. R is equal to square root of I, area moment of inertia, divided by A, cross-sectional area. So let's say a little bit, I will talk about radius of gyration, and I will define that because in mechanics of material course you will need that. So radius of gyration, they usually show with R, and for example Rx will be equal to square root of Ix divided by area Ry, radius of gyration respect to x-axis and radius of gyration respect to y-axis is equal to square root of Iy divided by A. And in order to calculate the buckling load using Euler formula, we will need that. And what is that? It represents the theoretical distance at which we could condense the entire area of a cross section into a narrow strip to get the same moment of inertia as the original. So, radius of gyration, it represents the theoretical distance at which we could condense the entire area of a cross-section into a narrow strip to get the same moment of inertia. For example, we have one cross-section, and this is X, this is Y. Radius of gyration will give one distance. We can condense this entire area A in one narrow strip like this. Okay, the moment of inertia of this strip respect to this x is equal to the moment of inertia for entire this area respect to x. So if we have cross section, the area of the cross section, for example A, and for example I want to calculate the radius of gyration respect to x-axis, and radius of gyration Rx is equal to Ix, moment of inertia, divided by A. So the radius of gyration is equal to square root of I over A. Now what is Rx? Rx is a distance, it represents a distance which I can condense this entire cross-sectional area to one narrow strip, and this narrow strip, now moment of inertia respect to this x-axis is equal to the moment of inertia of this cross-section respect to x. In which distance I should put that narrow strip, it is radius of gyration Rx. Now if I put this entire cross-section and in Rx and I condense that entire cross-section in one narrow strip, the distance of narrow strip up to x, it is Rx. The moment of inertia for this narrow strip respect to x is equal to moment of inertia for entire cross section respect to x. This is the definition of radius of gyration. So radius of gyration R is equal to square root of I, area moment of inertia, divided by A, area of cross section. Now I can define another area moment of inertia. Up to here I calculated moment of inertia for one cross section respect to x-axis and respect to y, respect to x and y. One cross section, something like that. Now we know how we can calculate the area moment of inertia respect to x and respect to y. But if I want to calculate respect to axis perpendicular to this cross section, for example the centroid is C here and the axis perpendicular to here to this cross section, for example Z, how I can calculate the area moment of inertia respect to Z. If for example it is kind of circular shape like this, the axis in the center, this is x, this is y, and this will be this direction perpendicular to this cross section, it is z direction. The moment of inertia respect to z, we call it polar moment of inertia. And in order to calculate polar moment of inertia, again, we will follow the similar way. For example, cross section, x, y, and here the centroid, another axis perpendicular to the C. I will assume one small element, dA. The distance from C to this element, for example, it is rho. The polar moment of inertia they show with J is equal to integration rho squared dA. Here, if this distance is y and this distance is x, I can write rho is equal to square root of x squared plus y squared, because it is one triangle. In this triangle, this is x, this is y, so rho is equal to square root of x squared plus y squared. If I plug here integration of, instead of rho, I will plug square root of x squared plus y squared squared dA. From here, this will be integration of x squared dA plus integration y squared dA. This is equal to, this will be I y plus this will be I x. So the polar moment of inertia J is equal to moment of inertia respect to x plus moment of inertia respect to y. J polar moment of inertia is equal to moment of inertia respect to the x-axis plus moment of inertia respect to y-axis. And this is very important because it has application. Let's write here J polar moment of inertia. Let's write here polar moment of inertia represents the resistance of the cross section to twisting about the z axis. So if I have my shaft, for example, this is centroid, this is x, this is y, this will be z direction. The polar moment of inertia represent the resistance of the cross section to twisting about the z. It will show us the resistance against the torque when I apply torque to this shaft. I resistance against the bending moment respect to bending axis. I resistance against the bending moment. So higher I means higher resistance against the bending moment. J polar moment of inertia, which is Ix plus Iy, it is resistance against the torque for one shaft. So higher J means higher resistance or smaller twist angle against the torque. Okay, I solve one example. Assume we have one U-shaped section. And it is symmetrical. This is 1 inch, 1 inch, X, Y, 3 inch, 3 inch, and this height it is 4 inch, this thickness again it is 1 inch. First step, I want to find centroid for this cross section. Then I want to calculate the moment of inertia respect to those axes passes through centroid. Centroid in the x direction, it lies on symmetry axis, so we know that x bar is equal to 0 respect to this reference axis. But how about y bar? I should calculate that y bar. First, let's calculate y bar. In order to calculate y bar, I will divide this to three rectangular. Rectangular number 1, this one, rectangular number 2, this one, and rectangular number 3, this one. And I will take moment of area respect to x. So it will be 1, the thickness, times 4, times the distance from center of this rectangular up to x, it is 2, plus for this rectangular 3, sorry, not 3, 6, the length is 6, times 1, 6, length, 1 thickness, the area, the distance of center of this rectangular up to x, it will be half, plus the moment of area for rectangular number 3 will be equal to, again, 1 times 4, this is area, times 2. This will be entire moment of area for this U shape respect to x is equal to summation of area 1 times 4 plus 6 times 1 plus 1 times 4 times y bar. From here I can find centroid location in the y direction. If you calculate this, y bar will be equal to 1.36 inch. That means the centroid of this cross section, it will be 1.36 above this x-axis. So if I show with another color, this will be xc, this point will be c centroid, and from centroid to x is equal to y bar, which is equal 1.36 inch. We found that. Now, if I want to calculate I, x, c, I will calculate the moment of inertia for this cross section respect to xc. That axis passes through centroid. Again, I have three rectangular. For rectangular number 1, for one rectangular, the formula, I prove it, it will be width 1 times the height 4 cube over 12. This will be respect to that axis passes the centroid of rectangular number 1. So for rectangular number 1, 1 times 4 cube over 12, it will be moment of area. Respect to axis passes through the centroid of this rectangular. And the distance up to x, it is 2 inch. Because entire height is 4, the half will be 2 inch. But I want to calculate respect to xc, so I should adjust to this axis. How I will adjust? From the parallel axis theorem, plus area for that rectangular, 1 times 4 times the distance between two axes. The distance between axes 2 from x, 1.36 from x. So this distance between two axes will be 2 minus 1.36. 2 minus 1.36 squared. This will be moment of inertia for rectangular number 1 respect to xc axis. Because it is symmetrical shape, number 3 is the same, I will multiply this by 2. For rectangular number 2 plus the width of rectangular number 2, it is 6 times the height, it is 1 cube over 12 plus, again this will be respect to that axis passes the centroid of this. It means here. And the distance up to x, it is 0.5. Now I should adjust to the red one, the XC. So plus area for that rectangular, it is 6 times 1 times the distance between these two. It will be 1.36 minus half squared. The answer for this will be 18.9 inch to the power of 4. Okay, if I want to calculate IYC, that will be equal to, this y is passes through the centroid of rectangular number 2. For rectangular number 2 respect to the y, the width it is 1, the height it is 6, 6 cube over 12, and this axis passes through the centroid of this rectangular, so you don't need to adjust, plus I will calculate to one of rectangular 1 or 3 and I will multiply by 2. For example, rectangular number 1 plus, now the width it will be 4, the height will be 1 cube over 12, but this is respect to axis passes through the centroid of this. Okay, it means respect to this axis. If I want to transfer to the y, the distance it will be 3 plus half. So plus area 4 times 1 times the distance between two axes. 3 from here, half of 1, it will be 0.5. So the distance between two axes, it will be 3.5 squared. For rectangular number 3, it will be the same thing, so multiply by 2. This will be equal to 341 inch to the power of 4. Okay, this is the way you will calculate area moment of inertia for composite section. Thank you so much for watching this lecture. See you next session. Bye bye.